Hey, okay, let's look at example 7.4 in the book. I cheated and already put some lines. We're supposed to draw the shear and bending moment diagrams. And so I'm going to do these lines so that we can see the kind of the events. So there's my shear and there's my bending moment. Straight as can be. Gotta love it. Okay, so the first thing we need to do is we need to replace the external forces with what they are. Oops, right here and right here. Okay, so how do we do that? So actually let's come in here, let's look at, for this purpose, this distributed load, we're going to replace with a single load right in the middle. Right, that's chapter 5 stuff, and that is 1.5 times 8, and it's located 4 off of there. Okay, so let's come in here, let's take the sum of the moments at A is equal to 0, so you have 20 times 6 plus 12 times, 14, right? Plus 1.5 times 8, that's the magnitude, and that's going to be 14, 24 plus 4, so 28. And that's going to equal D times 24, right? Okay, so that leaves us that D is equal to 26. Take my sum of forces in Y equals 0, and that's going to tell me that A is equal to 18. Okay, lovely. So let's come in here. This is 18, and this is 26. Okay, so now easy stuff done with. Okay, so now we're going to do the shear and bending moment diagrams. So as we just learned, the shear is the derivative of the distributed load, but from here all the way through up to here, we don't have any distributed load, which means it's constant except for these discontinuities, right? So it's like, consider this first one. So you have 18 going up, so I keep on doing this. If it's just a little section, you're going to have V there and your moment. So what must V be? V must be 18. So let's start here, and it's going to be 18, and it's going to be constant until we get to there. And then if you look at that, it's going to drop by 20. I can tell you that both from practicing a little bit, but also 20. Now you have your V and your M. Okay, so now that has to be, V has to be minus 2, which is 20 down from here. So this is 18. It's going to drop by 20 down to minus 2. It's going to hold that constant across to here. And now we're going to drop another 12, because now we have 20 and 12. So if you look at this, you have your V and your M. Sorry, and then, so in here, V is to be minus 14. So it's going to drop, boom, to minus 14. It's going to hold that constant to here. Okay, so now we have 18, drops there, comes across here, drops, comes across here. And now it has a distributed load, but it also has this 26 pounds. So it has to go up by 26. So, and again, because it's the same basic logic, 18, 20, 12, 26. So if you look at here, so this is right before anything happens. Your V has to go from, so you have 18 plus 26 up, 20 plus 12 down, and so you end up with a net of 12 up. It comes up here, so it goes up by 26, which is up to 12. We'll call that 12 right there. But then we're going to say, hey, you know what? dv dx equals minus w. And so we know that the slope of this is equal to minus 1.5. And so that then slopes down to there. And there you go. That is the shear moment diagram of this configuration of this diagram. So now we need to consider, that's a shear. Let's look at the bending moment. So what do we know about the bending moment? And again, we know that the area under the curve is the change in the bending moment. So what is the area under this curve? So it's 18 times 6, right? So 18 times 6, so that's a 108. This is minus 2 times 8, so it's minus 16. Look at that math that I'm doing. This one is minus 14 times 10, so minus 140. And then this one, it goes from 12 to 0, so 1/2 base times height, so it's 8. Half of this is 6, so it's 48 plus 48. So why does that matter? Well, because now we can come in here. The bending moment at this initial point is going to be 0 because there's no moment there, right? So we're going to start at 0. We went up by 108 in that area, so our bending moment goes up to 108, right? And then drops by 16, so it's not much, so it's going to come down straight down to there. So 108 minus 16 is 92, so we'll call this 92. And then it drops by 140, so it's going to go down to minus 48. So we'll call that right here. Straight line down to minus 48, kind of there-ish. And then it goes up by 48, so it's going to end at 0. But the key here is that now this is, again, so dm dx is v, right? So the slope of that. And so we know that this slope here, so it's going to increase faster earlier. And so it's going to be integration of that. So it's going to come up here like a second order curve up to that point. So there you go. So honestly, quite a bit easier when we're using these things and understanding this to go through and calculate these curves. That's that.